So today we will be discussing the finite element analysis aspects of railway bridge assessment, and we will focus especially on U-frame type of bridges, and we'll look at important aspects related to network rail assessment code and how we can use finite element analysis for the level 2 assessments of these type of bridges. So the contents for the webinar today are first I'll be discussing about the rail assessment philosophy, which includes linear static analysis or level 0 assessment, eigenvalue buckling analysis, then nonlinear analysis, both material and geometric, and then we will take some small examples, one of plate girder, simply supported plate girder, and the other will be a U-frame bridge, again simply supported and single span. So the most important aspect of the assessment is the live load. The live load that we consider for the assessment is known as the RA1 loading. As shown here, it's equivalent to 20 British Standard unit loading, and this is as per the 025 Network Rail Assessment Code. Now this the set of point loads which you can see on the screens can also be idealized as an equivalent UDL as per the table given in the assessment code. So sometimes we do use the UDL for assessment because it's simpler and less complicated. The basis of assessment is that we have a member capacity for different members, and we calculate the effects from the dead load. So whatever the effect capacity is remaining after subtracting the effects of dead load, we call it as an available load, for example, and then that available load is divided by the effect due to one static British Standard unit vehicle. So we saw the RA loading consists of 20 British Standard unit loadings. So we calculate the effect due to one BSU, and thus we get number of static BSUs. That number is then subtracted by 10, and we call it the rating of the bridge, or RA, also known as route availability. We should not confuse between this RA and the RA loading. They are fairly similar, but they mean different things. So RA, as in the rating, means route availability. So there are two types of RA that we need to check. One is the static RA and the dynamic RA. We just have to divide by the dynamic impact factor, which depends on the velocity of the train. So according to the assessment code, there are different specifications for dynamic factor, which we should select to calculate the dynamic number of dynamic British Standard units for a particular bridge. The RA loading, the rating RA, if it is more than 15, we just keep the rating as 15. That's the maximum rating in the assessment code. And if the rating of the bridge is less than 8, then the bridge fails the assessment. Greater than 8, it passes the level 0 assessment check. So level 0 assessment is simple linear static analysis. We calculate the capacities and we follow this graph shown here to calculate number of BSUs. For U-frame bridges, the most critical factor will be lateral torsion buckling, especially in the compression zone, in the mid-span area on the top flange and some part of the web at the top. We can expect some buckling, and to resist that lateral torsion buckling, the U-frame action it comes into picture. So the U-frame action, as per the code, can be only considered when we have the eye girders, the stiffeners, and the cross girders in a given section, and we can say that that particular section is a U-frame section which can resist lateral torsion buckling. The deformation of the top flange is a result of deformation due to the cantilever part as shown here, and the deformation due to any flexible spring. So depending on the type of joint, say depending upon the connection between the cross girder and the main girder, we can have a flexible joint or a rigid joint. So depending on the flexibility of the joint, there can be some additional deformations at the top, and also the deformation due to the bending of the cross girder. So all these three types of deformation comes into picture, and we get the net U-frame action, which is the main resisting factor for the lateral torsion buckling. Some typical checks that we do for U-frame bridges include the main girder checks, which involves bending at the center and web shear at the ends. Web and flange splices or splices should be checked. Cross girder locations, rail bearers, and some articulation like the main girder to cross girder connections, so like bolted or welded connection or riveted connection. Now, why do we need finite element analysis if we can do simple linear static analysis and find out the rating of the bridge? Then why do we need finite element analysis? Well, first of all, spreadsheets have been widely used for the assessment. Spreadsheets are good 2D calculation tools, but there is a limitation in their accuracy when it comes to buckling analysis especially. Then U-frame action, as we saw in the few slides back, U-frame action does provide good lateral restraint, but code can significantly underestimate the U-frame action, because as I said earlier, the code states that U-frame action can be considered for sections where you have stiffeners, cross girders, and the main girders in one section. So if there is no such type of stiffener or cross girder in one section, then U-frame action should not be considered. But that may not be accurate, because it has been seen through analysis that U-frame action is still very good when there is lack of stiffeners. Even in those areas, U-frame action can be good enough for resisting the lateral torsion buckling, and this can lead to a lot of cost saving in terms of maintaining the bridge, and also or if the code states that there is a failure in the bridge, then it can stop the engineers from actually destroying the bridge and constructing a new one there. Lateral torsion buckling checks, there is no standardized formula for which can be applied to all types of bridges. So this type of analysis needs a finite element analysis in the form of a full-fledged shell modeling, which we will see in our examples. And line beam models are very suitable for linear analysis, but when it comes to large displacement checks, then we need to go for more finite element and detailed computer analysis. Typical assessment flowchart. We go for linear static analysis first and have a good idea about the rating by doing the linear static analysis. Then we go for a buckling analysis, which we use the software or finite element software for such type of analysis. And for further checking the results, like yielding of the steel and large displacement checks, we do nonlinear analysis, and then displacement is checked for the bridge. Local buckling stress and stresses, and finally we get the rating, which is the worst case rating out of all these checks. Talking about buckling analysis, now similar to the linear static analysis, the way we calculate RA in the linear static analysis, a similar approach can be used for buckling analysis to calculate the RA or the rating of the bridge. So what we do generally in buckling analysis is that we have a stiffness matrix, we have a geometric stiffness matrix, and an unknown called lambda or eigenvalue. Now this lambda or eigenvalue can be calculated with respect to considering the geometric matrix for both permanent and live loads at the same time, or it can be calculated with respect to the live load geometric matrix only. Now for the rating, we calculate the rating as an effect of only the live load. So when we are doing the eigenvalue buckling analysis, most finite element software tend to incorporate both permanent and live load effects and give you the buckling factor with respect to both permanent and live load. But that doesn't really solve the problem, because rating is just the comparison with the live load effect. So In Midas, which is the software which we will be using for the buckling analysis today, we can separate out the effects and directly get the rating or the eigenvalue with respect to only the live loads. So as shown in the figure here, we have got permanent loads and variable loads, and we have got some available capacity for the live loads, and that's your buckling load. So whatever is the factor between the buckling load and the available capacity for live load, that factor is calculated, and that is actually lambda. So let's say the factor is 1.5 and we have applied 20 units of the loading. So the total units for the bridge will be 30 BSU, and we can then subtract it by 10 and calculate the final rating of the bridge. So that's how we do the buckling analysis checks. The key issue is calculating the load factor with respect to only live load. Then imperfections need to be introduced for considering the buckled shape, buckled condition. Now in the U-frame bridge, imperfections are introduced generally at the top compression flange of the midspan, because that is where we expect the buckling to take place most critically. Imperfections can be applied in 3 different ways. The first is as an equivalent force as a unit load on the top flange, and calculating the displacements coming out of that unit load, and then applying those displacement as a final geometry of the bridge. So when the bridge geometry is changed, you can then apply some other analysis types like nonlinear analysis and so on, and then consider the results based on the buckled shape. Now that method is based on Eurocode. There is another method where we apply prescribed displacement. We actually apply a displacement on the top flange, and then based on the displacement we have further deformations in the structure, and those deformations are then incorporated in the geometry, in the final geometry of the structure. Now one key thing for imperfection analysis is that it has to be a stress-free state, so just deformations and no stresses should be incorporated from the imperfections, just a zero stress state. Now the most efficient way of attaining or achieving the imperfections is directly through the eigenvector buckling mode. So in the finite element software, we note down the buckling modes which represent the lateral torsion buckling of the U-frame, and that buckling mode is used to extract the imperfections directly. So the software has a feature which can automatically convert the buckling mode into the deformed geometry, and then you can carry out further analysis on that buckled shape. So that is a much more efficient approach. Then finally we'll look at the nonlinear aspect of the analysis. So in the geometric nonlinear analysis, which is also used for, which is basically used for the large displacement checks, we apply the loads in steps. So first step, we apply all the dead loads. As you can see, this blue line, it's a linear curve. So the blue line represents the permanent loading applied, and then on the deformed shape. So finally, when we reach, say, up to this particular point here, the dashed lines, we start applying the RA1 loading or the assessment loading, and that assessment loading is then applied in 20 different steps, so that we get the result or the deformations for each step of loading, and each step of loading represents 1 BSU. So directly we can get from this curve, say that there is a certain curvature here, so we can assume that it reaches the final yield or the final strength of the bridge, the buckling load, and this is the point we match up the number of BSUs up to this point, and that will be our total effective BSUs, which we subtract by 10, and we get the final RA or the rating of the bridge from the nonlinear analysis. So all permanent loads applied by 100% in the first step, and then RA1 loading is applied step by step in the nonlinear analysis. And before doing this analysis, the initial deformed geometry of the structure should be assumed. So whatever imperfections we get from the buckling analysis, we start with those imperfections from the zero step or from the first step itself. And material nonlinearity can be considered sometimes if there is yielding occurring before buckling. So sometimes in the buckling analysis you will see that stresses are exceeding the yield stress. In that case, actually the material yielding is happening, and we need to consider that through an elastoplastic analysis. Usually the geometric material nonlinear analysis, that is combination of both large displacement and material nonlinear analysis, will give you a less value of rating, or the analysis will fail, or you can say the yielding will occur before the buckling, and so you will get a smaller failure load compared to what you get for geometric nonlinear analysis. Okay, so that's the theory behind the assessment. Just I've summarized the important points. Now we will look at some examples, and we'll use the software for calculating different rating problems by using buckling analysis and nonlinear analysis. So our first example is the plate girder example. This is the shape that we will be considering. It's an eye girder which has two types of loads applied, dead loads and live loads. We are assuming that 50 kilonewtons per meter for dead load and 50 kilonewtons meter for live load. And this 50 is equivalent to 20 British standard units, or let's say it is equivalent to the assessment vehicle. And we'll carry out buckling analysis. We'll find out imperfection or the shape resulting from the imperfection. And then we'll do nonlinear analysis on this example. So I'll take you straight to the finite element software and show you how it can be done. So that's Midas civil interface. What you're seeing on the screen is just a cross section. So just line elements representing the eye section. Now using these line elements, I'll create the shell geometry. So I can simply divide this the web into finer segments just to get the mesh right. Apply, and then select the web and use simple extrusion feature. Let's say thickness is 40 millimeters or 0.04 meters. And I'll use a mesh size of 0.2 meters. And let's say the total length is 10 meters, so 50 times. Apply. And I've got the web generated. Same thing I'll do for the flanges. This time different thickness. Apply. Okay, and we'll create the stiffener as well at the end. So just creating the stiffener here. So that's 12 millimeters again, and we can use the mesh tool. Okay, and here as well. Okay. So that's the fleshed view. That's how it looks like after applying the loads. Now, after applying all the mesh generation features. Now I'll apply some loads as a UDL. So loads element, and let's say it's a dead load, for example, minus 50 kilonewton per meter. And let's say it's edge load. So that's applied on the bridge, and the same thing we can do for the RA loading. Minus 50, apply. Okay, now I'll use some support conditions. So I've got few support conditions here. So that's a simply supported bridge. So dxt by dz, and a roller condition here. Right. Okay, so now we can perform the buckling analysis on this plate girder. So I'll go to analysis and buckling analysis control. Now we have to select the load cases that we want to consider for the buckling analysis. So basically for the geometric stiffness calculation, we use both live loads and dead loads, but the factor should be calculated with respect to only live load. The reason why I'm saying this is because, say if I use both the loads for calculating my load factors, so I make both of them variable. So both UDL and the RA loading as variable. Variable means the live load factor will be calculated based on the combination of both permanent and live loads. So carry out the analysis. Okay, so that's done. Let's check the results. So mode number 1. Okay, so I've got the top flange. You can see clearly the buckling is happening. Okay, and you have got a load factor of 0.6 as shown on the legend. You can see 0.6. So that means, according to this, it seems that the loading applied is too much, and the bridge is actually, or the girder is actually failing. But this is not true, because the rating is actually measured with respect to live loads. So if I go back, and now if I change the UDL to constant, okay, so that the geometric stiffness is still calculated based on RA and UDL, but now the factor, the critical load factor, will be calculated based on only RA. So you will directly get the factor for the for calculating the number of BSUs, or for calculating the rating of the bridge. Okay, so I've reanalyzed it, and now let's see what factor we get. So mode 1. Okay. Okay, let me okay. Yeah, so this model has got constant UDL and variable RA. So let's see what's the value of the buckling load factor. So you see, you get almost like 1.2, close to 1.2 with respect to the live load only. So it shows that we get a higher load factor when we consider the variable load to be only live load. So 1.2, if you multiply by 20 loads, we get 24 BS units, and so the rating will be 14. Now we can extract the imperfections out of this model. So we go to buckling mode shape and say update model with imperfections, and say mode 1, that's the buckling mode, critical buckling mode, and maximum value say 5 millimeters for the imperfection. So the maximum deformation will be 5 millimeters, and the other deformations will all be normalized. And after this, when we click on update, it will create another model, and we get plate updated this model. So we get the updated model just to show you if it is considered the deformation, I'll just measure the deformation somewhere near the midpoint. So you see it's roughly 0.0049 meters. So 5 millimeters maximum deformation. This is the geometry of the model which reflects the imperfection. So it is showing you the buckled shape, and now on this buckled shape we will carry out large displacement analysis. So to carry out the large displacement analysis, we first have to define our load steps. So first we define the sequence for nonlinear analysis. So load sequence. Our sequence will be first dead load will be applied on the structure, and then RA loading or the live load will be applied. Then after we have defined the sequence, we then define the number of steps for each load case. So if you remember, we apply the dead load at 100%. So we apply number of steps as 1. So the complete dead load is applied in 1 step. For the RA loading, for the live load, we apply some 20 odd steps and some extra steps just in case we want to capture the overall failure diagram. So even after buckling, what is the deformations for different loads steps. So we have divided it into 22 steps. So you can see each step is has 5% loading, and then finally the 2 steps at the end we have some 20% and then 50% extra load applied. So after this analysis, we can look at the results. So say the worst case node was, let's say, let me just extract one of the nodes here, say somewhere on the mid span on the top flange, say node number 229. Okay, so it will give you a tabular result of the deformations for a particular node. The node that we should select is the top flange node where the maximum imperfection was applied, and for each step you get the displacement. Now we should be interested in the dy or the lateral displacement for checking the lateral torsion buckling, and we can extract these values in Microsoft Excel. So we can just right click and say export to Excel. I've already copied them into Excel, so I'll take you to Excel now and we will see the result. So that's your UDL applied in step 1. You've got dy. We are concentrating on the dy value. Then load factor is 1 for the first UDL, and then we have 5% increment, 20 steps, and then that load factor is converted into actual loads, and we plot a graph. So we get something like this. The orange graph is for the geometric nonlinear analysis. Now if we wish to consider, say if we find out that the stresses after geometric nonlinear analysis or after buckling exceed the yield stresses, that means there is some material yielding happening. So we have to do a material nonlinear analysis combined with large displacement effects. So let's see how to do that. In our case, if you see the graph, I have performed the material nonlinear analysis already, and they are giving more or less similar results. That is, the failure is happening at the 100 kilonewton loads. But still, I will show you how to do the material nonlinear analysis. So open up the material nonlinear model. Okay. Right. So what we do is we go to properties and define a plastic material. So our material type is actually a elastoplastic steel. So we select the von Mises type of material model and define the plastic, the yield stress for steel. So that's, let's say, 275 megapascal. And once we have done that, we assign this plastic material to our initial material property. So we define material property as steel 275, and here in the plasticity data we define steel. So when the software does the analysis, the material nonlinear analysis, it assumes this material to be an elastoplastic material. Now in the nonlinear analysis data, we make sure that both geometry and material is checked on. So both large displacement and material nonlinear effects will be considered in the same model. And finally, we do the same, repeat the same steps. We get deformations in a table format and we copy paste in Microsoft Excel and we plot the graph. So you can see that this blue line represents the material nonlinear analysis, and that's the geometric only analysis, geometric nonlinear analysis. So from these two graphs, we calculate the failure load, say 100 kilonewton, and that gives us the factor required, or the load factor for the live loads. So 100 kilonewtons, actually 50 kilonewtons is only the contribution from the live load. So basically we can say that the factor for the live load is actually 1, and the number of BSUs is 20, and the rating that we obtain is 20 minus 10, which is 10. So from the geometric nonlinear as well as from the geometric material nonlinear, we get an RA10 rating for the bridge. So same concept we apply on a bigger model, on a U-frame bridge model. So in this model, we have applied few more realistic loads, self-weight, track loading, ballast conditions. This is a Z type of section. The main girder is a Z type of section, and we have got stiffeners at some equal intervals. And dynamic load factor for 100 mph speed is 1.71. So we will look at the results for this analysis. So the way of creating this model is fairly similar to how we created the plate girder. We start with a two-dimensional line model and then we extrude to create the full-scale model. So I'll just take you directly to the results for the buckling analysis. It's a slightly larger model, so yep. So so that's the overall geometry of the structure, just to focus on the different important components of the bridge. So we have got concrete. I'll double click to highlight the different portions. So concrete deck, steel plate girders. Now from the modeling aspect, for the assessment of the U-frame bridges, we model the main girders and the deck as plate elements or shell elements. Also the stiffeners are modeled as shell elements. However, the cross girders are modeled as line elements. So you can see these line elements here. And if there are some other sections, for example, there are some supporting rails here. So let me just hide the concrete so you can see. So I've just hidden the concrete on the top, and you can see the lines going longitudinally and transversely. Transverse lines are the cross girders. And you can see that not all the cross girder sections have actually got stiffeners on them. So as per the code, these sections should not be considered as U-frame. So in this model, you should actually be having like somewhere around 6 or 7 U-frame sections. But which may make the section, which may make the bridge a low rating bridge. But when you do a full detail assessment analysis on a FE model, you can actually see that all these cross girders which do not have a stiffener, they also participate in the U-frame action, and they're sufficient to resist the lateral torsion buckling. So let me show you how the buckling checks were done on this particular bridge. So for any dead loads or live loads, we have to consider the full factored loads. We have to apply the load factors for ULS. So I've applied, say, for the permanent load effects, I've applied some factors from the assessment code for self-weight, ballast, and track loading. And for the RA load also, I've applied some factors. Now these load combinations are converted into static load cases. So there's a simple feature in the software. You can convert static load cases from existing load combinations. And then under the buckling analysis parameters, we include the ULS permanent values as constant and the live load as variable. And this includes your load factors. And if the dynamic load factors are not included, you can later on divide by the dynamic amplification factors and find out the dynamic PSUs. So after the analysis, we get a buckled mode shape. Let's see the contour results. Okay, so you can see the girder on the other side here. The main girder has deformed or buckled, and the buckling load factor is 7.94. This is with respect to only the RA loading. Now going back to the presentation slide, we have buckling load factor 7.94, which is, you can say, 8, and number of BSUs is 160. Now this is equivalent to 92 dynamic BSUs dividing by this dynamic load factor, and thus it results in a rating much higher than 15. So we just limit it to 15 and say that this bridge passes the assessment. But this is not the final check. We should also check for stresses. If the stresses exceed the yield stresses in the after buckling, then we need to do material nonlinear analysis. Also, we should check for large displacement by doing a geometric nonlinear analysis. So let's see what results we get from geometric nonlinear analysis. So the same way, we create a model with imperfections. So update model with imperfections. In this example, I've used a 25 millimeter imperfection. So actually, you can do a parametric study with different imperfections, 5 millimeters, 10 millimeters, and there is a distinct variation in the graph that you will observe. The graph for the less imperfection values will be more sharper. So you'll have a clear-cut yield limit or a clear-cut failure load you can obtain. And the imperfections like 25 millimeter imperfections may give you a more curvature in the graph. So it is slightly difficult to actually interpolate the fine failure load in such graphs. So anyways, this is used for parametric study. You can put in different imperfection values and generate multiple models. And once you have generated the updated model, it will be in the same folder saying updated. And you can carry out the large displacement analysis. So the same way, just include your dead loads and live loads in sequence. Dead loads as 100%. Now in this sort of analysis, in this example particularly, I have not applied the factors for the dead load. I have applied the nonlinear analysis sequence on the unfactored dead load. So that's the SLS condition, and this is RA1 loading without factors. So if I look at the number of steps, I've considered 25 steps just to make sure I've covered all possible load values and all the deformations. So you've got first 20 steps are equal steps, and then I've defined some higher load steps here at the end. And after the analysis, I get the results, which is here. So you see 25 millimeter gives you a much a curved load displacement graph, So it's very difficult to clearly specify which is the failure load. So it's good to you can do a similar analysis for different imperfections and see what different graphs you're getting compared to the 5mm imperfection, where you got a more sharper contrast between the plastic and the elastic zones. Here you get very little difference, but still you can interpolate the values, and what you do is you first have to subtract the displacements coming out from the dead loads. So first subtract the effects coming out from the dead loads. Now my dead load and some initial part of live load, they are in the linear zone, so I can just simply compare the displacements. So say 1 unit RA displacement, which is corresponding to 5% loading of RA, that is 0.25 millimeters, which is simply subtracting this value, this displacement value, from the dead load value, and that gives me the equivalent RA unit for the dead load. So the entire dead loads can be converted into equivalent RA units from this graph by comparing the displacements between live load and dead load, and then you subtract that equivalent RA unit from the total failure load. So let's say my failure loads, static failure loads, were 220 BSUs, and I subtract that and I get the BSUs with respect to only live load. And then on this particular case, I apply my dynamic factors, my load factors, and finally I get the dynamic factor BSU, which I then subtract by 10 to calculate the final rating of the bridge. And again, the final rating is larger than, is quite large, and we can say it's 15. Our rating is 15 because that's the maximum allowable rating. And so the bridge is safe and passes the assessment check. We can do similar things for material nonlinear analysis and get the rating out. So that's how we do the assessment on the large scale model of the bridge. And that basically concludes today's session. So I will be answering your questions one by one. I've received a few questions here. So if you have any questions, you can ask me now and I can answer you. One of our attendees has asked the question that the code recommends the stiffener spacings in order to work out the buckling effects, such as moments, etc. So how can how is the FEM analysis more accurate? So this is exactly the point which I was trying to make earlier in the slides, why FEM analysis is needed. The code gives the formulations for linear static analysis and checking out the capacities mostly, and that includes a lot of conservative approach, considering U-frame action only for cases where you have stiffeners. So the stiffener spacing determines the spacing of the U-frames, and that can, and based on that we calculate the buckling, the moments for lateral, the buckling capacities, and that can sometimes lead to a very conservative value or very low value of rating for the bridge. And to avoid that, to get a more realistic approach, we actually model the bridge using shell elements or line elements, incorporate all the stiffness properties from the real bridge, and then we perform buckling or nonlinear analysis to obtain the load factor. And if the load factor is more than the RA loading, that means it's sufficient to resist the loads to come on that bridge. So that passes the assessment check. One of attendees has also asked if scaled eigenmodes can be used for both global and local shapes in the Midas. It's the scaled eigenmodes are entirely based on the buckling mode shapes. So if you have modeled all your elements properly in the full finite element model, then you get the buckle shape of the entire model, including all the local elements and also the global line elements. And the deformations are applied on the nodes of each element. So as long as you have modeled all the elements of your structure, you should have all the deformations incorporated. All the local deformations, local cross girder deformation, or let's say main girder global deformations, they all are incorporated in one in the final updated model. One previous question that I missed out earlier. If the plate girder model which I was showing earlier, we checked with first the permanent and live load factors, and we got some load factors 60% or something, and then when I converted to live load variable, and I opened another model. That's because initially I did not save the variable input properly, so it was still constant input, and that's why I thought I opened up a new model which I had already set up with live load as variable and constant as the dead loads as constant, and that's why, to save time, I just showed you the final result. So you can carry out the variation in the same model itself. It's just that I wanted to save some time. Another good question, how do we know that we have enough elements to give an accurate enough answer? Well, this is just a matter of experience and iterations. So depending on the type of model, type of bridge, we need to actually carry out 2 to 3 sets of analysis with fine mesh, with coarse mesh. It is always good to carry out the analysis first on a plate girder for the section that you are using. Say just model a plate girder and check with different mesh sizes, size of elements, and see if the load factor varies much, if you're getting a much variation in the load factors. So usually for the scale of the bridge which I showed, I had used a mesh size, an element size of 0.2 to 0.3 meters, 200 to 300 millimeters, and near the stiffeners, especially near the stiffeners, I had used 100 millimeter size, just to make sure that I get the local effects more accurately. So it is based on basically an iterative procedure. You have to check it yourself with sensitivity studies, what mesh size suits your bridge. Okay, so we are already out of time now, and if you have any more questions, you can email to uksupport@midasuser.com, and we'll be answering to your questions. If you need any free special demonstration on any particular bridge application, please contact us and we can visit your office or organize some customized webinar for you to show you the application areas of the software. So that's the phone number listed out here, so you can contact us by calling here. We have a support center in the UK. The address is also shown. And the video will be uploaded subsequently on our YouTube channel, and you will be supplied with the links later on. If you have any questions, as I said, please email to UK support. And that's it for now. Thank you for attending, and goodbye.